Hello everybody and welcome to STEM Clubs Hour, one of the final parts of POP24 here at Dynamic Earth. My name is Chris. We have got Ali here as well.
Hello.
We both work at Dynamic Earth full time. We're really proud to have been hosting POP24 along with STEM Learning today, and I hope that any of the sessions that you've seen earlier on today have really inspired you with all the amazing work that's going on across the planet to protect different ecosystems and biomes, and learn a little bit more about all the different STEM careers that there are that help us to protect different parts of our planet. So that might be engineering, that might be maths, it might be biodiversity. There are lots of amazing sessions that happen throughout the day that hopefully you got a chance to see. If you didn't, then they will all be on YouTube before Christmas. So I can't give you an exact date right now, but keep an eye on the YouTube page, and before Christmas they will all be up so you can catch up on anything you missed or watch them again if you really love them. So thank you to all of our contributors and providers across the course of today, and to ESRO, the European Space Agency and the UK Space Agency for their support in making this all happen as well. Now, speaking of space, today's session in STEM Clubs Hour is going to focus on satellites. So me and Ali are going to talk a bit about satellites today. If you joined POP23 last year, we also talked about satellites a bit last year as well, but we're going to talk about different satellite stuff today as well. So we're going to be talking about them because there are loads of different applications of satellites that help us to protect our planet in lots and lots of different ways. So before we get stuck in, there are some activities that we have developed that you can do alongside the session today. There is a STEM Clubs Hour 2024 pack about Earth observation on the STEM Learning website, so you can have a look at that and try some of the activities along with us. Or if you're just doing science activities in your STEM club already, you can have us on in the background. You can do your own science activities that you've already got planned. There's other science activities from other providers like climate detectives from the European Space Agency, for example, and the Eden Project, and lots of other providers who've done other sessions. They've got stuff up on the website as well. So whatever you're doing, I hope you managed to get lots of hands-on exciting activities done today. So, as I said, we are going to be talking about satellites, and Ali is actually an expert astronomer. So he works for the Dynamic Earth in our planetarium. So he is a massive space expert, and I thought that if we're going to be talking about satellites, then we should probably know exactly what a satellite is. So Ali, I believe that you are going to be able to tell us how we might be able to launch a satellite into space and how we keep it up there.
Yeah, okay, so what is a satellite? We use the word a lot. Maybe the first thing to talk about is that you do get natural satellites. I mean, our moon is technically a satellite of planet Earth, but usually when we use the word satellite, we are talking about the man-made things, the human-made objects that we are putting in space around planet Earth, and it's starting to get quite crowded up above our heads. Now, we do have a video of a launch of a satellite. It's not a realistic video, because what I've done is I've made a little clip of what it might be like to launch a satellite from Edinburgh, and we're going to actually just sort of go through this in stages, because there's a couple of key things to note about satellites. And where we're going to start out at Dynamic Earth, we do get a nice view at sea level, but the trick with a satellite is really to be moving very, very fast. Now, just how fast, I will get to that. But when you start from sea level and you need to launch yourself into space, space is not actually that far away. It's just 100 kilometers up above our heads, maybe 200, so that you're not skimming the very top of the Earth's atmosphere. Now, the getting into space part is technically quite easy, but it's the staying in space that is really, really difficult. Now, with that launch, we need to use rockets, because aeroplanes will take us up to maybe 10, 12 kilometers. Passenger jets, that's as high as most human beings will ever get from our home planet. If you want to get higher than that, you can use things like helium balloons, and we did have some researchers talking about their Arctic balloons for measuring stuff very high up in the atmosphere. They're only good for about 30, maybe 40 kilometers up above our heads. But to get into space, you need to use rockets, because there's not enough air, and the rocket is the only thing that's going to let you get going faster and faster. Now, once you get into space, you need to keep accelerating, and it will take about 8 whole minutes to get going fast enough to cheat planet Earth's gravity. Now, the planet Earth is always trying to pull us down. That gravity is pretty strong. It's what's holding us to the floor here in this room. But if you get going quick enough relative to the planet, so moving sort of in this direction above the atmosphere, so there's nothing to slow you down anymore, planet Earth's gravity will try and pull you down, but what it's going to do is going to pull you and you will end up falling around the planet. It's all about going incredibly fast. If you get going quick enough, you won't lose height anymore and you will just fall all the way around planet Earth. That's what we call being in orbit. But all we're doing here is falling with style. That's what it means to be in orbit. Now, the speed that we're talking about, 7.5 kilometers per second. Now, that is just a number, but to give you an idea of how fast that is, it's Edinburgh to London in less than 80 seconds. That's how quick we are talking about here. So every satellite that we're talking about today, the things that you'll see in the next clips, these are moving incredibly fast, faster than bullets from guns, and that is worth bearing in mind.
So you'll be able to see that just now, and that will show us going up then towards near Earth orbit, is that right?
Low Earth orbit is the bit of space that's very close to our home planet. So that also tends to be where you send the humans as well. We do also have a video of the active satellites that are in orbit around our home planet as well. Now, those satellites, there are quite a few up above our heads today. Last I checked, there are more than 10,000 active satellites up above our home planet today. That's quite a lot. Now, in 2020, there was only just over maybe 2,000 or so satellites, so that number's gone up a huge amount in just the last few years. Most of those satellites are actually communication satellites, and they live in a place called low Earth orbit. Now, that low Earth bit that we just spoke about, that's relatively close to us here on planet Earth. It's maybe anything up to about 1,000 kilometers away from planet Earth. That's considered low Earth orbit, and things in low Earth orbit are moving the fastest out of all the satellites. You can go around the planet once every couple of hours or so, maybe even every 90 minutes. And in that bit of space, you have the International Space Station. The Hubble Space Telescope is there as well. And all the Starlink satellites, that's communication satellites. One of the reasons it's getting busy up above our head is that's where they're all parked as well. Now, as you get a little bit higher, you get to a medium Earth orbit. And there, the satellites are traveling a little bit slower. And they can orbit the Earth once every 6 hours, maybe every 12 hours. And that tends to be where you place things like the global positioning satellites, things like that, for helping us find our way on planet Earth. You don't need quite so many satellites in a medium Earth orbit. And then beyond that, you have a very special ring of satellites around the whole planet. This is pretty far away. Here's that video coming in now, which is fabby. Now, if you look closely at the video, you might need to turn up your screen brightness on this as well, because every single dot is the position of an active satellite today. Now, you'll be able to see a blob down in the middle. That blob is where planet Earth is, and it's surrounded by a large number of satellites. That's where that blue blob is coming from. But if you look very closely, you can see around the edge of that screen, that is the ring that is called geostationary orbit, a really special place to park satellites. If you live on that line, it takes you exactly 24 hours to orbit our home planet. And because our planet is spinning once every 24 hours, it means that those satellites appear to never move in the sky. It's a very handy place to put observation missions and also things that will broadcast satellite TV, for example, because you can point your satellite dish at a fixed point in space. Now, if you look close, you can see the medium Earth orbit satellites moving as well, and the ones that are right up above our planet in low Earth orbit, they are moving the fastest. But like I said, it's starting to get quite busy up there. And what you have to bear in mind is that for every satellite that you can see in this video that we're showing you here, there's a lot more leftovers. There's debris, there's satellites that don't work anymore. Every so often they might collide, and when you smash bullets into bullets, that creates a whole bunch of other fast-moving bullets in space as well. So space scientists will spend a long time, a lot of energy tracking all of these various bits and pieces up above our planet. It's getting to the point where we have to alert satellite operators to potentially move these satellites to avoid them getting smacked into at some point down the road. So there's quite a few things up there. And even though it looks like everything should be hitting everything else, it's still mostly empty space. That visualization does make it look a little bit more crowded.
I suppose that visualization is also going to make everything look a lot bigger than it actually is in reality. Yes. So some of those little blue dots presumably are only like a few centimeters.
Oh yeah, I haven't made them big enough for us to see them, but yes, compare that. So you can just make out cities cities on the same scale. So yeah, I can just about see Edinburgh in there.
Yeah, so there's a huge amount of stuff moving around our heads. Now, you mentioned GPS, you mentioned satellites as well. Is there any other application from satellites that we rely on day to day?
Well, I mean, you've got communication is really invaluable. I mean, one of the reasons Starlink is there is to give everybody very fast internet access. But that needs a lot of satellites because they're in low Earth orbit. You need loads of them, thousands of satellites, because that means you've got constant coverage of every piece of planet Earth. The global positioning stuff is incredibly valuable. I use that when I go hiking. But maybe the Earth observation stuff is maybe the most exciting because there's research missions that I'll use to study the rest of the universe, but you can turn those same telescopes back towards planet Earth and you can do an awful lot from a long distance away. So
yeah, so I think like a lot of people, they hear the word satellite, and if they know what it is, I guess they know that it helps us communicate on planet Earth, but I think people don't realize the sheer array of stuff it allows us to do to live our lives here on Earth, and how space science and all the engineering that goes into making this equipment isn't actually just for learning about what's going on in the far reaches of outer space, but it helps us to learn a little bit about what's going on here as well. So we are going to be thinking a little bit about Earth observation, what we are observing using satellites on planet Earth. And the first thing that we're going to be thinking about, actually, before I go into that, I just want to say that there is a little Q&A bar at the side. So if you do want to put any questions through on the chat for me and Ali, I'll try and keep an eye on it throughout the session, and I'll see if there's any that either or both of us are able to answer. It might be likely that Ali is able to answer more of it if it's anything to do with space, but we will see what we can do. And so feel free to submit some questions to us throughout the session. Now, the first thing that we are going to be looking at is satellite tagging. So we are going to be talking a little bit about how we can put satellite tags on different animals and how we can then get a picture of what these animals are doing. So the first thing that I want to show you is a picture of one of the printouts that you might have. So this is a grid with coordinates. Now, if you know how coordinates work, feel free to get started on plotting those coordinates. If you're not sure, it's pretty straightforward. That first one that says B8, so you go along to the letter B, you go down to number 8, and then you just put a cross in that box. And then the next one, D6, do the same, go along to D, go down to 6, and put a cross in, and then join them together with a line. Keep doing that as I'm chatting, and then we'll see if I've given you enough time to plot out the route of a particular animal that lives in the sea and that you would find off the east coast of North America. So, as you are doing that, I'm going to talk a little bit about why we do that. So a satellite tag is safely attached to animals, lots of different kinds of animals, and we'll have a little look at different kinds of tags in a moment. And it helps us to understand where animals are traveling. So this might mean that we can then paint a picture of where they're migrating to and when they're going there. And it gives us an understanding of how animals move around the world, in what numbers they're moving around the world as well. And that means that we can then put plans in place to help with conservation efforts for these animals. So, for example, if you've got a sea creature moving around different parts of the ocean, you can get an understanding of just how far they will travel, but you can also get an understanding of how often they're coming up to the surface. So we can, we've got a little example here. So this is real data of an animal that was found swimming around the east coast of North America. And it actually starts to draw what looks like a little bit like a self-portrait. So Ali made a lovely visualization using real data from satellite tagging. And what do you think this looks like? Because to me, this looks like exactly what the animal is. At least it does now. I think it's, if we pause
I had
it
to
there.
pause it here because it's about to ruin its own artwork, but that's just right.
Yeah, then we can see that there's an animal here, and you can tell that this looks like a shark. And this was actually drawn by a great white shark called Breton. Now, you can see then it looks like Breton then zooms up the way, goes over some land, which is not what actually happened in real life. Why does that happen?
Well, the GPS tags, they're really good, but they can be inaccurate, and they can also take a little bit of time to get an accurate fix. So if the shark isn't spending enough time on the surface, you might miss an accurate ping, and it looks like it's cutting the corner when in reality the real path would have been a little bit more complex. So we're just showing you the data that we actually have, but it's part of the fun of doing real science, because you've got to work around little issues like that. You've got to try and figure out where it's been, even if you don't have the data points to convince you otherwise.
Yeah, and I mean, also worth pointing out related to that is that was data taken over the course of 2 years. So that shark was not actually traveling around the North Atlantic quite at that speed.
Yes,
So.
It's actually 4 years.
4 years.
Where I paused it was 2 years, and it had a ping like 2 days ago. So if you want to see where Breton is, you can. And I think it's more than 50,000 kilometres travelled.
Really?
So it kind of puts me to shame a little bit with my walk.
To be fair, I think that Breton is also like a 13-foot long great white shark, so twice the size of you as well. So easier to cover more ground if you're enormous like a great white shark. We've seen that by tracking that data, we can see exactly how far a species like great white shark can travel. And that is also something that we can do with lots of animals that live in lots of different areas. Now, there are a few different grids, different coordinate grids that you have got in the resources that you can download. So if you want to try and create some coordinate maps and coordinate pictures of your very own, you can try and investigate some animals that might be tagged, and then you can plot out coordinates and then get someone to try and draw them out. See if you can come up with any other ideas of animals that might try and draw a self-portrait using satellite data like Breton the great white shark. Now, I had a nice question in the question and answer list, which is from Stead's STEM Club, and that's one I might pose to you, Ali. Are there any satellites that we can see with the naked eye from the ground?
Yes,
Yes.
Plenty. Maybe the biggest and most famous of all satellites is the International Space Station. That thing is the size of a football pitch, so it is huge, very good at catching the sunlight. Unfortunately, it's not up and visible for us tonight in the UK, but in about a week's time, you will have a chance of waving, I think there's 7 astronauts currently on board the ISS. It tends to be low down in the south, and you'll see it moving from right to left, but it's a very bright dot. You've got to get the timings just right, and there's websites that will let you know exactly when it's going to be visible. And if you're lucky, you will actually see that bright dot fly into the Earth's shadow, because the timing and the angle of the sun have to be just right. Even if you can't see the ISS, there's always a chance of seeing just normal satellites catching the sunlight. So maybe the first half an hour after sunset, you've got a chance of seeing plenty of satellites up above your head. So they'll be moving slow and steady points of light, not blinking like aeroplanes, that kind of thing. So good luck spotting.
Excellent. And on that, they've also asked what the biggest satellite we can see is. So
I think I've just answered that one already.
I think, it is also the ISS. Biggest human-made satellite, just to confirm that the moon is definitely bigger than the International Space Station.
Biggest natural satellite. Yeah, I think we didn't really talk about the size of satellites. So to give you an idea, they can vary an incredible amount. So the ISS is the size of a football pitch, but it was stitched together from multiple different things, multiple launches. Some satellites are not much bigger than a loaf of bread. They can be incredibly small. On average, it's about the size of a small car, and some of them are as big as school buses. So if you imagine the amount of effort to launch these things up to those very high speeds, is quite a task.
Yeah, okay, so great questions. Thank you, keep them coming. Now, on animal tracking, we've also got another nice visual, a nice video, which shows lots of different animals moving around. So we saw Breton, the great white shark. Here is a visualization of lots of different species. Ali, what can you tell us about what we're seeing here?
This is a fabby clip. It's from the NASA Scientific Visualization Studio, and it's data from what they call the Arctic Animal Movement Archive. So this is 40 million data points of various species of animal, and it's about 30 years worth of data. and they've squished it all together so that any date or month throughout the year, you can see where all of these data points lie, and it gives you a really nice sense of how all these animal populations are moving with the time of year, with the seasons, that migration pattern. Now, a lot of this data might not have been collected by satellites. Some of it's 30 years old, so it's very likely some poor scientists were out there collecting diligently in the field all of these positional informations. Not every tag talks to satellites, so you might have to go out and recover those tags to see where that creature has been. So it's just a really nice way of seeing all of that data on the planet. And this is not the only place you can get data like this, so scientists are doing their very best to keep all of this migratory information online and accessible so people can make really pretty visualizations like that.
Yeah, and you can see the sheer range of animals as well. So it had terrestrial mammals, so mammals that we find down on the ground, raptors, shorebirds as well, and it gives you an idea of just the sheer scale of movement of life on Earth. And if you imagine individually tagging lots of different animals, and then in the past, if you had to actually track the movements without relying on much satellite data, that's a really tricky task. So the fact that we now have satellites to give us an idea of that scale of movement, that scale of animal biodiversity as well, it's a really helpful piece of kit, I guess, to have if you've got satellites that help you to study this. Now, I'm sure some of you are wondering what satellite tags actually look like, and I mentioned that they'll look different for different animals. So we'll be able to show you a couple of pictures of different satellite tags. So you should be able to see A, B, C, D, and E, a few different satellite tags. You can't quite tell how big all of them are, but I'll give you an idea for what all of them are. So Ali, do you have any guesses? What tag like
the one on the left
A.
The one on the left looks big, so I'm thinking large creatures, elephants maybe?
Well, so A, larger animals. So we've gone for marine animals here, but a tag like this, you're right, it's a little bit bigger, a little bit chunkier. So you put it on an animal that's a bit bigger and chunkier as well. So you can stick this onto an animal like a whale, like a turtle, like a seal, and you can track where they are going. But then compare that to tag B, and you can try and work out as you're watching as well where you might find tags like this. Any ideas what you might use this for?
Kangaroos, put it in the pouch.
Well, I think if we look at the C in the background, that's a little bit of a clue. So it's not a kangaroo, but this, and I wouldn't necessarily have expected you to get that it was an acoustic pinger, but you can also use little tags like this on some sharks. Sailfish is an example of another marine species. When I say acoustic pinger, this is the technology here is essentially that this tag is very, very small, and you're not going to be able to ping the signal from this tag all the way up to the satellite that's moving around above us. So it'll go up to a piece of kit floating on the surface of the ocean that will receive it acoustically, so through sound going up through the ocean, transmits through the water, and then that's what pings it then up to the satellite up above us. So very clever extra step there to help us track some smaller species. What about C? It's a bit like a Tamagotchi.
Is it designed for the back of a bird or something, like big birds maybe?
Well, let's see. We've got terrestrial animals, so not so much birds, but this is just going to be animals that we find on land. I can't tell you exactly which animals on land, but we are going to be talking a little bit about some animals that we can track on land in a little moment. D, that looks a bit like a microphone. It
does. It looks watery. Is that a float thing?
Yeah, a few of them are watery. And to be honest, that's also because it's really difficult to track animals in the water. So the ocean is so massive that for us to physically follow the animals around is very, very tricky. So if you can put stuff on the animal, like this one, so it is a float satellite. So again, sharks, it feels like we're tagging lots and lots of sharks, but this is a temporary one. So when it does come off, then it will float at the surface and they can be collected. E, this is another marine one.
That's a strange one. It just looks like one of those AAA batteries with an aerial. So I have no idea on that one.
It's a little bit more sophisticated than a AAA battery with an aerial on it, I believe. They've added a light sensor onto it, so it can actually help us get an understanding of the movement of animals that dive to different depths of the ocean. So a lot of tags, when the animal goes near the surface, that means that the signal can ping up to the satellite. But if the animal's spending a lot of time down in the depths, then the signal can't reach that high. But by recording the data on here, you can also then see how deep down the animal is diving because it's got a light sensor attached to it. And we've also got a picture of a turtle. Oh, we might do. Oh, maybe not.
Really pale turtle.
A really pale turtle, that might not have popped up. But we will stick tags onto turtle shells, and they will stay attached to the turtle shells for a little while, and then eventually they tend to come off. So a lot of the time the tags will be on the animal for a little while, but they will run out of battery, or they might end up becoming sort of unfixed from the animal, and that means that the animal swims off without a tag. But we've got often sort of a few months, a few years worth of data of what that animal has been doing. So that gives you an idea of what those tags look like and the kinds of animals that we put tags on. But as I say, oh, there's that turtle. The turtle's back. So they managed to identify it. So you can see the example of the tag on our turtle's back. So this is a juvenile loggerhead sea turtle. And turtles travel huge distances as well. So again, it's really useful for us to be able to track animal movements using tags like this because they travel huge distances in very inaccessible areas, for humans at least. So as I said, we had a lot of chat there about animals in the ocean. So lots of sharks, lots of diving animals, turtles. But what we are going to have a little look at next is how we can monitor some animals on land. And this isn't actually by tagging them, it's more just by looking at pictures. So what we're going to do is we will bring up a picture of some elephants, which has been taken from a satellite. So in this picture, there's going to be a few elephants taken from above, and what you'll need to do when it pops up is try and count how many elephants you think you can see. Now, it might not look like the highest resolution image. Here we've got it now, so you might need to peer quite closely at it. But bear in mind, satellites are quite high up in the sky, so the fact that they're taking these pictures at all is quite impressive. So here we go. Now, Ali, how many elephants are you tracking down here?
Okay. Just let me just take in the scene. So I'm seeing. No, those are cars on the road up there, so I'm not counting them.
Yeah, so you can see a track at the top.
There's something top right. There's loads by the water, so I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2 mini elephants. What are baby elephants called? Calves?
Calves. Yeah, calves. Mini elephants is nice, though.
How many did I say? 8 plus 2 little ones. 1, 2, 3, 4, 5. What's that? Maybe 13 plus 2 small? That's my guess.
15. So are you thinking 2 calves?
Yes.
And 13. Okay, well, we can have a look. So if I move on to our next one, then we should be able to see the answer. So here it is actually 18 total. So you were close. There are 14 adults and 4 calves, or mini elephants. So you correctly pointed out, though, that up near the top, there's a rock, there's a shadow. Those look like they could be some elephants taken from above, but actually those are slightly different, which is tricky for us to tell the difference. That's why we need a lot of scientists to look at this imagery and start to understand what the animals look like when they are taken in these photos, and then we can get a picture of how widely spread they are, for example. So we are using AI more and more, artificial intelligence more and more, to try and start counting how many animals we'll see in pictures like this. But you can't just put a computer program there and say, do it. You count those elephants, because they need to know what the elephants look like. So we need the scientists to kind of work out, oh wait, I think that's an elephant, that's a rock, that's a shadow, and then use that to train AI programs and to understand these data sets, and so they can start going through all these images and start counting just how many, for example, elephants there are. So that means that it's slightly easier than just sitting there counting if we can use AI programs to do it ourselves. And when you consider an animal as big as an elephant, in South Africa, you can get satellite imagery that covers sort of 5,000 square kilometers on a clear sunny day, and you could potentially count a lot of elephants in that. There are thousands of elephants across Africa. So we've been looking at how we can use AI to learn a little bit more about them. If you want to try and do some of your own animal spotting, there is a project called Walrus from Space. So the British Antarctic Survey, who you might have heard from earlier today, they have been looking at how we can count walrus from satellite imagery. So walrus are an example of an animal that like to spend time on their own and don't really want to be disturbed by people. They also live in places like the Arctic, which are quite hard to get to, quite hard for people to go and stay for a long time, particularly in the remote areas where walrus live. So they've opened it out to the public to try and spot some walrus in satellite images to help them get a better understanding of just how many walrus there are and understand walrus populations so that, again, we can work out the best ways to do conservation efforts. Now, elephants and walrus are both pretty big. And I want to talk about an example of how we can count another animal which is not as big as these two. So we can also get an understanding of where we would find penguins as well. So the next image that we're going to bring up, it features satellite imagery, but it doesn't actually have the penguins in it. So here we have got Antarctica, and the little circle shows some zoomed in spots around Antarctica. And you might not be able to see them in itty bitty detail because the images are a little bit smaller, but on 4 of these images, there's actually big swathes of penguin poo because they do not clean up their mess when colonies move around different parts of Antarctica. So even if you can't see in itty bitty detail, you might be able to see in the bottom right, in Ninnis Bank, there is evidence of penguin poo. So Ali, can you, for example, see?
Just right in the middle. It's
Right
the darker thing.
Yeah, so you've got the sort of big blocks around the side, and then there's what looks like a little streak in the middle, right in the center of that image of Ninnis Bank, and that is all penguin poo. So even though individual penguins are quite small, and the mess they leave behind is so big that that's actually a good way of identifying where we'll find penguin colonies. And that's useful in many ways. So the other spots where there are spots of penguin poo, even if you can't quite see, we've got some in Yule Bay, so a little bit west of Ninnis Bank. We've got a big splodge in Cape Gates. Ooh, trying to zoom in a little bit for you there. And we've got a little bit in Cape Gates as well. And potentially most interestingly, we've got some up in the Brunt ice shelf. So you might be able to see that the Brunt ice shelf looks a little bit different. Oh, there we've got a zoom in on Ninnis Bank, so you can see that streak of poo in the middle. So that is just mess left by a penguin colony. So that gives you an understanding of what the satellite imagery is able to pick up on. And the Brunt ice shelf one is a really interesting one because as we move around the coast, these look nice and clean. When we get to the Brunt ice shelf here, the poo mark, for want of a better word, is down in the southeast. So you'll be able to see there's a little bit of a dark splotch in the bottom right, the southeast of this circle. And that's actually on the mainland. So you can see everything else is breaking away. And you might have heard stories about how the ice in Antarctica is melting, the ice is calving off the coast, and so we're losing quite a lot of ice down in Antarctica because of the effects of climate change. But by using this satellite imagery, we can see where the penguins are, and we can say with confidence that the penguins were not on any of the bits of ice that broke off. So even though it might seem funny that we're looking for evidence of poo on the satellite imagery, it's actually giving us a really good understanding of where we're going to find colonies of penguins. And particularly for Antarctica, it's a really remote, inaccessible area. And so scientists don't live there all year long. Lots of researchers will go there to research stations like Rothera, and they will stay there for weeks or months. But we don't have any permanent residents other than animals like penguins. So if we can use satellite imagery to learn a little bit more, then that is a really useful tool for us. Let's see. Oh, I had one nice question here, by the way, from Space Enthusiast, which I like. Are all 10,000 satellites in space working?
Yes, that was I tried to get the most accurate number I could, so it's between 10 and 11,000, and they're called active satellites. So those are the ones that are doing what they're supposed to do, they're where they're supposed to be, and they maybe have enough fuel to do these emergency avoidance maneuvers if things were going to collide. In terms of tracking the debris, the leftovers, I think the numbers are a little bit scarier. So there's more than 40,000 chunks that are bigger than 10 centimeters, and they're all actively being tracked. If you go down to pieces bigger than 1 centimeter across, there's more than 1 million flying around up there. So yeah, it depends what you call a piece of debris. Some old satellites get put in what are called graveyard orbits. So their geostationary orbit, for example, gets a little crowded, and you don't want to leave the old satellites just hanging around there. So they get moved a little bit further away, and they will just get left there. And it's likely they'll be there for a very long time to come. The ones that are lower down, they will eventually enter the Earth's atmosphere, so they will burn up. And it kind of cleans itself. It's not perfectly clean, because obviously you're raining down little bits of satellite. Most of it does burn up, but that is just something else that we have to keep an eye on in the future, because you don't want too much of that stuff raining down on anybody.
Yeah, well, that's actually a really nice point. So thank you very much, Space Enthusiast, for that question. So the point about the debris and the impact that humans have on the orbit around planet Earth, and we can also think a little bit about how we can monitor human impact on planet Earth itself, because I'm seeing a lot of the effects of human impact down here on the Earth's surface. So this is when we're going to look at another activity that you might have prepared. It's all about the impact on habitats. So we'll bring up a picture which has got some habitats that different species might like to live in, and you don't need to be able to read all the text on the screen here. Really what you want to look at is the 3 different circles here. So we've got the yellow, the red and the blue circles. And I want you to consider 3 different animals that live in the Amazon rainforest. Now, the Amazon rainforest is incredibly biodiverse, a huge amount of life there. But we are going to think about tree frogs, we're going to think about macaws, so parrots, and jaguars, big cats. So 3 very different species that live in these spaces. And we want you to think a little bit about the adaptations that these animals would need to live in the rainforest. So you think about the adaptations the animals would need, the lives they need to live, the food they would need to eat, and then we've got little summaries here of these different spaces, and so we can identify which bit might be best suited for the different animals. So at the yellow area, lots of fruit-bearing trees, very dense canopy, and a few small rivers. So Ali, if you had to pick between a parrot, a frog, and a jaguar that might want to live in that yellow area with the tall trees, a nice dense canopy, which one might it be?
I'm going to go with parrots.
Yes, that would be a great space for the macaw, particularly because of the tree cover and the canopy layer of the rainforest. Great. So now we've got the red and the blue, we've got the frog and the jaguar. And the red area, the plant coverage is really, really dense, and there's a lot of rivers flowing through these spaces.
That sounds froggy to me.
It would be pretty froggy, I think. Yeah, so if you said frog at home, well done. And that leaves one for the massive blue area, the large uninterrupted area of rainforest far away from human impact. So that would be a great space for our jaguar. So well done if you managed to clock that is where those species would like to live. Now, what I want to do is show you the change between 2001 to 2019. And we can go back and forth a little bit and see how the insides of those circles have changed. So, when we go back to 2001 to 2019, you can see that there is a huge change in the satellite imagery here. So I'll go back to 2001. If we look at the blue area, for example, which is a huge uninterrupted space back in 2001, then 2019, you start to see these different shapes. Now, any idea what those different square shapes might be?
Farms, plantations, maybe?
Yeah, plantations. So a lot of these plantations are likely to be oil palm plantations. So oil palms are the plants which you might have guessed we get palm oil from. So if you have heard of palm oil, it's in a lot of stuff. It's in a lot of food. It gives food a lot of creamy texture. So you get it in a lot of chocolate, for example. But you also get it in things like soap. So it's really useful. But when we're cutting down rainforests on a huge scale to make these plantations, you're going to get a lot less biodiversity. And a jaguar is a lot less likely to want to stay in a place like this. And then if we look, for example, at the yellow and the red ones, this is 2001, but we change to 2019. You can see the amount of change in less than 20 years. Now, obviously, these three species that we've chosen, they have all their likes and dislikes. They have different diets. They like levels of humidity. They like some peace and quiet away from humans. So you would find them across lots of different parts of the rainforest. So actually, these changes are going to impact lots of species in lots of different ways. And we can see the scale of the change by monitoring it using satellite imagery. So what we can also show you next is actually a time-lapse video of some deforestation in the Amazon to help us understand the scale of that change. So here you can see between 2017 and 2020, so towards the latter end of that time frame that we were talking about before. And there you see a massive change in quite a short amount of time. So in 2020, we saw that there was a huge amount of deforestation that took place, which gives you an idea of just how much these areas are changing. So this is a great example of how satellites can be used to monitor human impact on habitats as a way to understand our impact on our environment and how we might be affecting the environment of animals in different parts of the planet. So these changes that we see over a really long period of time allow us to understand what we might need to do next to make sure that different species and different environments can survive the impact that they're subjected to. Now, I'll double check if we've got some questions coming through. How often, Ali, do satellites collide?
Thankfully, not often. There was one notable example, an Iridium satellite crashed into a Russian one, and that was back in 2009, I'm going to say. Right. I can't remember exactly off the top of my head. And it's not good news when it happens, so we want to try and minimize it as much as possible. What's been a little bit scarier is in the last 10, 15 years or so, people have been shooting missiles at satellites. China did this and actually released a huge amount of debris. And everyone who worked in the space sector was kind of like, you didn't need to do that to test that weapon, because the more debris up there, the less accessible space is going to be for us, because the more of these bullets you create, the more you risk that chance of another collision or something else fragmenting. They call them fragmentation events. But if you've got something, even if it's very small, when it's traveling at that speed, it can knock a big chunk off of you, and you might lose a satellite that way as well. So it's just something we're ever more aware is going to be more of a risk in the future. So thankfully, not too often, but you do get some near misses. I think NASA look for anything within maybe 10, 50 kilometers, something like that. So that's quite a long distance. Yeah. But they will alert both satellite operators and they will ask them to try and move their satellites to minimize that chance of a collision.
Yeah.
So not just NASA, lots of people.
Yeah. Lots of people tracking what's up there and what's likely to bump into something else. But if the most recent example you could think of was 15 years ago, then I think that hopefully...
It's quite rare you get a big smash like that. So.
Thank you for that question. And then we we've got a couple of other questions. Can satellites tell the type of trees from STEM Club? That is a good question. I know that there are satellites like biomass is one, and I don't know the ins and outs of all the engineering and technology in biomass, but it will actually measure the biomass, so the sort of mass of the trees, and so it will manage to take measurements of how big the tree is. So my guess is that they would be able to, at the very least, identify how tall or small the trees are to an approximate degree. Do you think that sounds reasonable?
Type of trees might be a little bit hard to do precisely from space, but you can definitely tell the health of the trees, I think. You can tell if the trees are maybe a little bit parched. The satellites will be very good at measuring that moisture content as well. So, but that's a great question. I might have to dive into that and see if you can tell.
Yeah. Now, okay, so next up we are going to try one of our other activities. This is to help us understand a little bit about the ways that we can measure, again, another threat to forest environments, and particularly the risk of forest fires. So there is an activity that you may have in the pack, which is all about making a sort of little, what's the word? It's sort of impersonation, a little version of a forest fire by having a printout of a map of Scotland and then popping a hand warmer underneath this map. Now, we would task you with trying to tell where the hot spot is underneath the map. You might want to put it on a soft surface so that it means you can get the map a little bit flatter with the hand warmer sitting in the cushion or the blanket or something underneath it. And as it warms up a little bit, if you hover your hand on top of it, then you should be able to identify where the heat is. And this is similar to what satellites are trying to do to identify where different wildfires are breaking out. But instead, they are using infrared, or IR. So we've got a little video of a version of this activity that we did using an IR camera, which we can show you. So here is our map, here is our little IR camera, and you can see there is a spot which I think is somewhere, potentially in the Cairngorms, I want to say, when we look at it here. So even though we wouldn't be able to see it from how far away we are, by using IR wavelengths, the instruments and the sensors on the satellites can help us to identify where these fires are breaking out. Now, we use infrared sensors on satellites. Are there other kinds of sensors that satellites can use to see what's going on the surface?
There's a whole lot of stuff you can use. I mean, radio waves, so radar mapping, LiDAR, where you're using kind of laser light to bounce things off. There was that Aeolus mission that was using an ultraviolet laser, I think, and that was able to measure wind speeds in the atmosphere just by watching that laser light scatter off of particles. So it's all really clever, and every year that goes by, the satellites get a little bit more capable, and the same is true for the missions that are looking further out into space too. Those infrared detectors get better, and with every pixel of light that you have, you can do quite a lot of science with each pixel. So a lot you can do.
Yeah, so thankfully the wildfires that you would be sensing if you're holding your hands over the maps, or that we saw in the video there, they probably wouldn't be that big. That took like about 10% of Scotland. We're not looking at wildfires that are quite that scale, but you might have seen huge wildfires breaking out in areas like California, like Australia. A lot of places are vulnerable to the effects of an increasing temperature, and with droughts as well, becoming more common because of climate change, then it means that the risk of fires like this are higher. Now, one thing that's really cool is that there is a constellation of satellites being planned, so a big network of satellites being planned called FireSat, with plans to launch the first one in early 2025. And this constellation of satellites is going to be monitoring areas for wildfire risks. So they're going to be looking at where areas might be facing the risk of forest fires, and I believe using infrared to help identify these hotspots, and then using AI as well. So when a certain threshold is met, then these programs can essentially contact people who need to be contacted to say, there's a high risk the fire is going to break out here. We might need to evacuate people. We might need to plan what we're going to do if we're facing this hazard, which is a really clever application that's going to potentially save a lot of lives as fires can break out. Now, we've only got 12 minutes left, and we've got a couple more things that we want to talk to you about, including one more activity, which is all about hurricanes. Now, you mentioned using UV wavelengths to see the wind speed and particles in our atmosphere and how things are moving around, and we're going to be talking about that as part of this. So the risk of hurricanes is not a risk that we're really facing in the UK because we aren't in a location where hurricanes can really form and crash into us. Because hurricanes form when you get a lot of humid air over warm ocean areas. And so with temperatures increasing around the world, we're more likely to end up with warmer oceans. And that means that we're more likely to get this humid air warming up, and warm air will rise. As it rises, the water will essentially start to be released from the air, and clouds will start to form. And if you're particularly unlucky in areas of low pressure, and as the clouds are forming and moving, a storm starts to form, and then we end up with a hurricane building up. Now, and there's an activity where you can simulate this, a hurricane bowl, and we can bring up a video of one that we did earlier. It's a simple one to try and see what is happening. It's easier if you do it potentially in pairs. So you can have a stirring implement. You can see the lovely modeling of a spoon that we've chosen here. And what you need to do is use your stirring implement, make sure you've got some paint on hand. You get someone to stir and start to create those winds that are spinning around. So small, fast circles in the middle to create an eye of a hurricane is ideal. Then get someone to add some white paint into this storm, and this is the water being released and forming the clouds. And the clouds will start to spin, your storm will get thicker, your clouds will get thicker, your storm will get worse and more severe. And you can spin it faster and faster as the clouds start to collect and form and thicken as your storm gets worse and worse. This is what's happening in a hurricane. You just have to imagine you're doing it above a hot ocean. Now, at the beginning of this year, the National Oceanic and Atmospheric Administration, did I get that right?
I think so.
NOAA in the US, they predicted that we were going to see some severe hurricanes in the Atlantic this year because we've been able to monitor different weather patterns using satellites. And that includes using the ultraviolet sensors, where ultraviolet is reflected off dust in the atmosphere. And so that's one example of how we can measure different weather patterns and different things that feed into weather as this dust moves around, as winds blow things around in our atmosphere. And we've also got a few visuals of some real hurricanes that hit North America earlier this year, because the other side of the Atlantic, they are a lot more susceptible to being hit by weather like this. So fingers crossed these visualizations will work nicely. The first one that we're going to look at is one that happened in June, I believe, called Hurricane Beryl. Now, Hurricane Beryl here. What can you tell us about this one, Ali?
So what you're seeing here is from a NASA satellite called the GOES spacecraft. It's looked after by NOAA, and it's GOES East. So it looks at the whole of North America and South America. So it's sitting at geostationary. It's very far back. And what they've done is they've cropped the satellite image to just show us the hurricane as it's proceeding through the Caribbean here. You can just about make out the eye wall forming down in the center there. It's hard to get a sense of the scale of these things, but you're talking at least hundreds of kilometers across for some of the bigger hurricanes. And the eye wall in the middle where the winds are fastest, that can be really destructive. If you're wondering why you can see the clouds at nighttime when there's no sunlight illuminating the clouds, we're using infrared light from these satellites as well. So it just gives you a chance to keep following that storm system, whether the sun is shining on it or not. So they're quite fascinating videos, but you have to remember that in some of those towns and islands in the location of these things, there are people frantically trying to get away or make their homes safe, because the stronger these storms get, the more energy that there is for these systems to develop, the more damage they can cause. So this one, I think, held the record for being one of the earliest Category 5s ever. So the strongest type of hurricane.
So one of the things that we're seeing patterns, weather patterns changing, and we've actually found that hurricanes like this wouldn't be expected to form when they formed. So Beryl forms sort of June time. Typically, we would expect hurricanes to form in the area that Beryl formed in later in the year. So actually, it meant that there was less time potentially for people in these areas to prepare, because this isn't typically something that they would have had to face in past years. Then after Beryl, we had another hurricane. So this was Helene, sorry.
Yes. Helene was another really strong one. Only made it up to Category 4, but it did a lot of damage because it slammed into Florida. This is taking a completely different path. Now, the people who are hurricane experts, they'll know that month to month, the sort of average track that a hurricane wants to take will vary, and it's all to do with loads of different variables to do with wind patterns and where that extra energy is, where that humidity is, what the seasons are. And so depending on the time of month, it changes what the hurricane might or might not do, and you have to track it with as much detail as possible, because they can change direction relatively quickly depending on what other storm systems or fronts move in on top of the hurricane as well. So it's a bit of a movable feast, and the game here is to get very good at alerting the people who are going to be in the path of that thing. That's the tricky thing to get right. I think this one was quite destructive. And then unfortunately, 2 weeks after Helene, we had another one called Milton, which we also have the visuals of for
Yes, we can
this.
see what Milton
Which
did
managed
as
to
well.
hit south of where Helene hit as well. So feeling very sorry for the residents of Florida because of this. Now you have to remember, it's not just the winds where that eye wall is very destructive, but hurricanes bring so much rain with them that you will see some intense flooding underneath the worst of that rainfall. And you also have what's called a storm surge. Now the hurricane itself can allow, think of high tides, but those high tides can come even higher thanks to the wind speeds, the low pressure of these systems, just sort of pushing water onto land. So if you're living on the coast, it's kind of a triple whammy. You've got the wind, the storm surge, and the rainfall all at the same time. So one of the reasons why we need these satellites, because it gives us the information to try and alert people. And luckily we did manage to get a lot of people to safety that might have otherwise been at risk with this one.
Yes, which was really urgent, because Hurricane Milton was one of the fastest intensifying Category 5 hurricanes. So it went from 80 miles an hour to 175 miles an hour in the space of 24 hours. So, I mean, we don't even get winds as fast as 80 miles an hour in the UK ever, really. So the fact that that was the minimum that then more than doubled is pretty incredible. By using the data and predicting when this is going to happen, and as Ali says, then the key thing is that we are then able to evacuate people, make sure people get to safety. Now, we've done a lot of talk about clouds, and I've noticed on our Q&A, Craig's STEM Club has asked, what if it's cloudy? Can satellites see through clouds? Now, this is an issue when we're trying to take pictures. So when we were looking at elephants, that's going to be a problem. If it's a cloudy day, you can't count any elephants. So we can't see through clouds using the photos, but are there other ways we can kind of see through the clouds?
Yeah, so if you're just using visible light, a normal camera, you are going to struggle to get through clouds, because we can't look through clouds ourselves. But if you have infrared detectors, then you have a chance of being able to see the water vapor itself, or find the right flavor of light that you can look at that allows you to see what you really want to see. The problem with infrared light is it can be harder to get a very sharp focus. One of the reasons why the Webb telescope was so big was we needed those infrared eyes to be very sharp. So that's why we had to give it a very big mirror, because it's longer wavelength light, so a little bit harder to get the same quality of picture. But yeah, infrared light will definitely help you see through clouds.
Yeah, that's a really good question. So we are getting towards the end, but there's one or two questions I can, potentially pose to you, Ali. I don't know whether we'll be able to answer them. One of them is, what are some of the solutions to space junk?
That's a great question, because we're looking for people who have the right ideas, because there's a lot of stuff up there. It's moving incredibly fast. It's quite tricky to get the satellites up there in the first place. So people have been speculating about harpoons. You send something up with a big harpoon on it, and you shoot something, you grab it with the harpoon, and then you try and pull it down to where it's either going to burn up in the Earth's atmosphere, or maybe you can leave it in a graveyard orbit. But that harpoon might be creating more debris. Some people have talked about using nets. Other people are talking about things that are clever enough to go and hug the satellite, move it to where it's going to be safe, and then go and do that with multiple satellites. But this is hard to do, because we're talking more than 40,000 pieces of leftover junk bigger than 10 centimetres alone. So there's a lot of work to do, and it's only going to get messier up there. So yes, if anyone has any amazing ideas, getting rid of space junk is one of those tricky problems that we're going to have to solve soon.
Yeah, okay, and this might be the last question that I pose to you.
Okay.
And again, you might not have a perfect answer for it, because it's how do you get a job working on satellite technology? So I know that you don't work on satellite technology, but you might know some folk in the business.
I do have some friends, my pals at the Royal Observatory. They literally build infrared detectors to go on the backs of telescopes and go into space. They work at the UK Astronomy Technology Centre. I think the key is to stay keen, to stay nerdy, read up on everything. Wikipedia is full of information about all of these different types of satellites, and I know Scotland produces a huge number of satellites every year, so they're crying out for people with the expertise to understand these things, to be able to get in and tinker with them, come up with new designs that can solve the problems that we need to solve, see those things that we can't quite see from space, because there's always going to be something else to figure out. So yeah, good luck, and just stay keen. I think that's the trick there, is just find everything you can and dive into it.
Yeah, and I think that's a really nice note to finish up on, because there are lots of ways that we can try and find solutions, and hopefully you've gotten a bit of an understanding today of how important satellites are in solving some of those problems, mainly because of the way they can help us understand the scale of the problem that we're facing and the scale of the solutions that there are to all of these different ecosystems, different impacts, different habitats, all of these things that we can use satellites for. Now, we are going to finish up there, but thank you so much for joining us today. I hope you've enjoyed POP24, and thank you so much to all of the other providers who have contributed today as well. Ali and I are going to leave you with a lovely video which was taken from the International Space Station, looking back down at planet Earth. A lot of astronauts report the overview effect of understanding the importance and the awe of outer space and the amazing opportunity we have to live on our little planet that we call Earth. So I hope you enjoy that video, and thank you so much for joining us today.
Thanks so much.
Bye-bye.